Hi guys, my name is Swadhin.
I'm Lucky.
And I'm John.
Our project name is Identifying Metastatic Cancer Through Deep Learning. For this project, we have taken the case of metastatic cancer for breast, and it's a very common cancer throughout the world with 2 million cases last year. The dataset for this task is the PCAM dataset with 220,000 color images of size 96 by 96 pixels. And each of these images is from a histopathologic scan of lymph node. A positive label means that the center 32 by 32 pixels have a cancerous growth, and a label of 0 means there is no cancerous growth in the center pixels.
So for our model, we trained a four convolutional layer model. So there's 4 convolutional layers followed by 4 fully connected layers. And to address overfitting, we have data augmentation such that the input data is randomly horizontally flipped or vertically flipped. And we also applied dropout regularization and batch normalization to speed up learning. And for our model, we used PyTorch because it allowed us to do rapid prototyping, and we developed it on Microsoft Azure Deep Learning VM. And since it is a binary classification problem, we used the binary cross-entropy loss function.
So to improve our model, we optimized by going after the hyperparameters that would give us the best output. So we started with batch size. With a batch size of 32, we trained till we got 97% accuracy on the training set, and then we increased the batch size in multiples of 2 and decreased them, and we landed at 16. That a batch size of 16 gave us the best test accuracy. In the same vein, training over 30 epochs, we started with a learning rate of 0.001. And we increased and decreased and landed at 0.0005 as the optimal learning rate.
And then after we got the best hyperparameters, we found this paper that told us that switching from atoms to standard gradient descent would provide better generalization. We tested that out and we found that it was true. So after we moved to train with SGD after atoms, we actually hit our top accuracy of 97.2%.
To better understand the data, we explored the importance of color, of the staining of the images on the model performance. Our intuition was to remove the color since we couldn't find anything that pointed to the fact that the color had an input. But when we trained with the grayscale images, we saw a degradation in the tested accuracy. So we concluded that the color does add to the accuracy of the model.
Finally, for error analysis, we used saliency maps from the final convolutional layer. And when we were comparing the true positives and the false positives, what we noticed was that it was really good at finding a specific feature of cancer is that they leave their environment to migrate to other parts. And when they do this, they gain a more rounded morphology. And that seems to be what our model is good at identifying. So if you look at the false positives and the true positives, you'll see a lot of this kind of protruding 3D looking cell that looks like it's moving away from the neighbor. And the true negatives and false negatives, they look like a lot more of a flatter morphology without the rounded 3D popping out.
So for results and conclusions, we achieved a final test accuracy of 97.2% on 22,000 images. And we learned quite a few things about hyperparameter tuning, using research papers like SWOTs. And we also tried some experiments like the grayscale input, which did not work for us. And we believe we have achieved significant progress given the time and resources. For future work, we would like to use pre-trained models from AlexNet and VG16, which have been trained on ImageNet. We can use activation functions like ELU, exponential logical unit, and use some scaling techniques like progressive resizing for increasing our test accuracy. Thank you.
Thanks.